Okay, hello there. My name is Zachary Kottman, and this is for ME3260 System Dynamics and Vibrations, and I'm going to be presenting the solution to the last problem on the first homework set. So in this problem, we're given a system of masses and springs, and we are asked to find the equations of motion. So here I have drawn the system that we're given, 2 masses, 3 springs, and I'm going to start by defining a coordinate system or systems. M1 will move x1, M2 will move x2, and the equations of motion that we will find for this one-dimensional system where we have 2 masses that can move, we will have a system of 2 differential equations. So we're going to have a differential equation for mass 1 and a differential equation for mass 2. And I'm going to talk about how I like to go about solving these problems. This might be a little different from class, so maybe it'll help, maybe it won't. Depends on how you see things. So what I'm going to do is consider mass 1 and what possible forces it can feel. There are no external forces here, so we don't have to worry about those. So pretty much the only forces we have to worry about are those that are applied to it through K1 and K2 springs. So I'm going to consider first, the first possible motion is a displacement of x1. I always consider positive displacements. Helps me just keep things straight in my head and on my paper. So displacing x1 positively, here I have drawn a picture. This is the equilibrium state. This is where x1 has been displaced positively. K1 has been stretched. K2 has been squished. So there's going to be a force from K1, the stretch spring. It's going to want to pull M1 back by K1 times x1. And then K2, the squish spring, is going to want to push M1 back, K2 x1. So this equates to forces on M1, negative K1 x1 minus K2 x1. And I'm going to write this like this, K1 plus K2 times x1. So that's considering a positive x1 displacement. These are the forces M1 feels. And then I'm going to put that into our differential equation. Then I'm going to consider the other displacement, the other possible displacement, x2, positive x2 displacement. So if we displace x2, we stretch K2 out, and we squish K3. And I'm focusing on the differential equation for M1 right now, so I'm considering what happens to M1. What does M1 feel when X2 is displaced? What does M1 feel when this spring here is elongated, is pulled? Well, it feels a force in that direction, K2 X2. So a positive K2 X2. It doesn't feel anything directly from K3, so there is no K3 in the differential equation for M1. So this positive force we will put in the differential equation for M1, K2 X2. And those are all the forces. That's the sum of all the forces. And of course, Newton's law, the sum of those forces equal the mass, M1, times its acceleration, which will be x1 double dot. Double dot is the second time derivative with respect to the position x1. X dot would be the first time derivative, the velocity. X double dot is the second time derivative, the acceleration. Okie dokie. So there's our differential equation for m1. And now we will consider the differential equation for m2. So once again, we will first consider what m2 feels from a positive displacement of x1. When x1 is moved forward, k2 is squished, k1 is elongated. m2 is not going to feel anything from k1 directly. m2 will feel the force from k2 being squished, and it's going to want to push m2 that way. So what we're going to get is a force on m2. It'll be k2 x1. Remember, positive displacement x1, k2 squished, it'll push on m2. So for displacement x1, we get k2 x1 force on m2. And then we will consider a displacement of x2. x2 displaced positively, k2 elongated, k3 squished. So k2 will actually pull back on m3, or m2. We'll get a negative k2 x2. Well, I put the arrow there, so I won't put the negative sign. k2 x2. And then k3 is squished, and it'll be pushing backwards on m2. So we'll get k3 x2. So this is a minus k2 x2 and a minus k3 x2. So I'll write that as a minus k2 plus k3 x2. All right, and that will go in our differential equation, minus k2 plus k3 x2. And then that summarizes all the forces that m2 can feel. And those, again, will equal ma, m2 this time, acceleration x2 double dot. All right, so those are our equations of motion. That wasn't too bad. But notice here, you might notice, you may not, but we can rewrite these in a slightly different form, which I personally like to use, and that is in matrix form. k1 plus k2. You can see, you can consider x1, x2 here like a vector multiplied, operated on by the matrix k1, k2, 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 k3. So that's what I'm writing right now. Give me some space here. And then this we can also consider the mass matrix multiplied by the acceleration vector, x1 double dot and x2 double dot, with some zeros in the corners. All right. So in this type of deal, I actually like this a lot for doing more complicated systems. Just you can easily expand this to systems with more masses and more springs. Kind of fun. And in fact, I'm going to do one right now because this was rather simple, maybe a little bit boring. So I'm just going to go ahead and do a more complicated system. Not much more complicated. I'm just going to add one more mass. All right, so we'll have 3 differential equations. One for each mass. I'm going to give it coordinates x1, x2, x3. Really like the whiteboard. I can just erase and move stuff around so easily. All right, so once again, we will sum the forces on each of these given all the possible displacements. There's no external forces, and we'll set those equal to MA. I'm going to do it a little bit differently. I'm not going to draw the extra diagrams, and I'm going to do all the effects of x1 displacement, and then all of the effects of x2 displacement, and then all of the effects of x3 displacement, rather than saying what are all the effects on M1, what are all the effects on M2, what are all the effects on M3, and you'll see what I mean here. But let's get started. So first I'm going to consider a displacement in the positive x1 direction. So if I move x1 positively, K1 will be elongated, K2 will be squished, so K1 will pull back on M1, K2 will push back on M1. So for M1, we're going to get a negative K1 plus K2 times x1 like we did before. And then once again, if we displace x1 positively, we're squishing K2, so M2 is going to feel a push from that squished K2. So it's going to get a positive K2 x1. M3 is not connected to K2 or K1, which are affected when you move x1. So x3 does not feel anything directly when you displace x1 positively. All right, now let's go to x2. If we displace x2 positively, first we'll talk about M1. M1 will feel a pull from K2. X2 displaced positively, K2 will stretch out and want to pull M1 along with it. So we'll get a plus K2 x2 here. And we'll do M2 displacing x2 positively, stretch K2, so K2 is going to pull back on M2, squish K3, so K3 will push back on M2, so we get a minus K2 plus K3 x2. And then when we displace x2 positively and squish K3, what happens to M3? Well, M3 feels a positive push from the squished K3, so we have a plus K3 x2. And you see how I'm doing all the x1 displacements, all the x2 displacements, all the results of x2 displacements, and now I'm going to do all the results of x3 displacements, where before I did everything that could happen to M1, everything that could happen to M2, and then it would, if I followed that order, it would have been everything that happened to M3. This is a little quicker. So I displace x3 positively. In my mind, I imagine I can see that K3 would be stretched, K4 would be squished. Neither of those are attached to M1, so M1 will not feel anything directly from a displacement of x3. M2 will feel a positive pull from the stretched out K3 as M3 moves forward, stretches K3, tries to pull M2 along with it. So we have a plus K3 x3. And as x3 is displaced positively, K3 is extended, K4 is squished, K3 will be pulling back on M3, and K4 will be pushing back on M3. So we will get a negative K3 plus K4 x3. And then for each one of these, we set them equal to MA. This was M1, X1 double dot, M2, X2 double dot, M3, X3 double dot. And then in matrix notation, which is fun, we'll have negative K1 plus K2, K2, 0, K2, negative K2 plus K3, K3, a 0 here, K3 here, negative K3 plus K4. And then vector x1, x2, x3 equals matrix M1, 0, 0, 0, M2, 0, 0, 0, M3 on vector x1 double dot, x2 double dot, x3 double dot. Some interesting things here. We have a symmetric matrix. You can kind of see the pattern. It's like these are the springs attached to M1. These are the springs on either side of M2. These are the springs on either side of M3. And then, anyways, interestingly, if we make all the K values and M values the same, and then this can apply to some situations in physics. And consider maybe a system of atoms or something, or a system of molecules where all the masses of the atoms or molecules are the same, and then you have electron bonds between them with spring constants that are the same, or something like that. There's lots of situations where you might have a lot of oscillators with constants that are the same and masses that are the same, and they're coupled. And that actually, if we set all the K values equal to each other, set all the M values equal to each other, we can pull the K and M values outside of the matrices and find some really simple, it becomes a really simple eigenvalue problem. We can find the modes of the system, etc. And I'll show that right here real quick. Not all of it, but a little bit of it. So we could write this as K times negative 2, 1, 1, 0, negative 2, 1. Oops. And then you do just K over M, and that's the frequency of oscillation in a system with one pendulum or one mass and spring or something. You might have something similar to K over M as your frequency, and if you have a system of multiple masses and multiple springs, if they all have the same mass and the same spring coefficient, your frequency of oscillation again is going to be K over M, and this is becomes an eigenvalue problem, and it's pretty fun to solve. I haven't done it in a while, so I'm not going to do it here, but that's it for this problem and the kind of more complicated version of the problem. Thanks for watching.